Well, good morning, good afternoon, good evening to 30 different countries around the world for tuning in to the latest AFuzion Tech webinar series. We do these once a month for all of our clients and friends worldwide. And this morning, it's morning for me, about 7 o'clock, and many of you too. This morning, it's really my pleasure to have my colleague and friend, Dr. Marcel Beemster from Solid Sands, really giving you incredible knowledge about object-oriented software, C++, how to optimize your software to really be safe, reliable. Even if you're making cell phones, Microsoft products, you want safety. Look, my cell phone, hell, fire, everything is safety critical these days, okay? So I'll do a quick introduction. We'll talk about OO briefly, and then I'm going to turn it over to Dr. Beemster, who will speak for about 20 to 25 minutes and start thinking about your questions, okay? We'll open it up at the end in 45 to 50 minutes for Q&A, and see that little question box there? Just type in your questions. We'll do our best to get them all. And if you registered, which obviously you did because you're listening to this, you can watch the recording anytime over the next 60 days and share that and just enjoy that as well. So with that, let's go ahead and begin, shall we? First, quick introduction of what is AFuzion. I think most of you know Solid Sands, our friends over in the Netherlands. Let's talk briefly about safety critical standards and C++, and then orienting C++ objects, what that really means, and then our Q&A session. So AFuzion, as you know, we're the world's largest safety critical services company. We train 90% of the world's 500 largest aviation companies in optimizing software, systems, safety, aircraft. We also have 55 full-time engineers worldwide working right now on optimizing your process. They use the AFuzion templates, checklists. We provide mentoring services, and we actually do the engineering, the software development, the architecture, system safety assessments. And if you're flying on an aircraft or you see a military aircraft in the sky, it's got our solutions on it. And Solid Sands, Marcel will introduce a little more detail. They're the world leader in C++ compiler library testing. They're based in the Amsterdam, Netherlands, with many staff members, all very senior and capable, but they work worldwide as well. They also sell SuperTest. It's a test suite for software with a almost 4-decade track record, and also SuperGuard. It's a requirements-based test suite for C and C++ standard library. With that, let's begin. Now, objects have many forms. There's tangible things within a system. There's interactions, sharing, calibration. Objects have roles, and there's incidents. Objects let us abstract from the problem domain. They really enhance our reusability. And ask yourself, folks, really, is your software getting easier or more complex? What do you call software that never changes? Bye-bye. Your software will evolve. What version of the iPhone, Android, are you currently using? Exactly. So OO, object-oriented software, gives us that ability. So there's basic types of objects. We've got interface, control, and entity objects. Obviously, interface objects let us interact with the world, where control objects, they provide functions like schedulers, process managers, and entities can store information, transactions, histories. Now, what is OO? Essentially, you can see on these next two slides, OO software has classes that group related data structures together. Objects let us hide information. We can have inheritance, polymorphism, and ability to replace objects with subobjects. And more powerful capabilities is overloading, using the same symbol for different purposes or different arguments. For example, adding a float or an int or strings to concatenate. We can convert types from one to another. Let a source value change to a different target value. This lets us abstract from the hardware abstract from the problem domain, and really give us reusability. Lets the software engineer be less concerned about the CPU architecture, the real-time operating system aspects, and work on the application domain. We also have dynamic memory management. In the old days, anybody with 20 years plus experience remembers we avoided dynamic memory management. Well, with C++, with OO, we like it. We need to embrace it, but we have to be careful, okay? Remember, C++ is very powerful. It's like a shotgun. Remember that board's true strap? Yeah. C is dangerous. C++ is more powerful. Well, we can also have virtualization. That's abstracting resources to emulate or simulate execution. Very, very powerful technique. Now, there are some vulnerabilities, and this is what we're really focusing on today to really optimize and improve your software to make it safer. Yeah, we got to do some things. We got to recognize that OO and C++ are vulnerable everywhere because compile time and runtime covers everything. So before compilation, statically, have we really represented our objects correctly? And then at runtime, do we know what's happening? Can we affirm determinism? And today, how many of you are working with artificial intelligence? Ooh, everyone's using it, let's be honest, okay? Well, that introduces more vulnerabilities. So we use standards like DO, which means document 332 in aviation. If we use OO in aviation, we must use this. But folks, if you're not doing aviation, you still want to read this. It's, in my opinion, one of the best tutorials ever written on safe C++. So we need to address those vulnerabilities and provide evidence that we've resolved them. So let's look at those vulnerabilities, shall we? Number one, inheritance. That's right, it's always the relatives, right? Well, LSP, list cost substitution principle. Do we have safe inheritance? Have we checked for unused code? Ooh, yeah. So, folks, what does that mean? Well, we need to exactly consider multiple inheritance and avoid that. And then parametric polymorphism. We need to ensure that we have consistent data. With aviation, we have a thing called, source binary, ensuring essentially that the compiler, and this is where Solid Sand comes in, is correct. So for level A, our highest level, can we do that? We need to verify all types. And overloading is powerful, but it's also dangerous. We need to consider ambiguity, name collisions, okay? Then, what do we need? Well, explicit, not implicit type conversions. And type conversions themselves, we implicit coding rules, and DO 332, medical, automotive, require a coding standard for casting and converting. We have to show that we meet that coding standard. And it's more, folks. It's more than simply MISRA C++. So 3 more exceptions. We want to localize exception handling. Instead of, here, catch this, throw it, raise it, let somebody else solve your problem. No, let's be honest. Admit it's our problem. We caused it, we fix it. And absolutely avoid unchecked exceptions. Now, dynamic. We talked about this 5 minutes ago. The D word, dynamic. Be careful. We need to employ object management, garbage collection. We have to think about what's happening at runtime. We can't check for this statically at compile time. So we need to be aware and use metrics assessment to ensure that we avoid memory starvation, exhaustion. And then virtualization. We need to verify each virtualization layer. That means ensuring tracing of all interpretations, okay? So folks, what do we do? Well, first, recognize you're here, you're watching this, you're busy, all of you. You're investing an hour, you know that C++ is powerful. We've got vastly more sophisticated design capabilities, increased portability, much better reusability. We can abstract ourselves out of the CPU, out of the low-level C code with objects. But we need to think, do we understand the risks of C++? Go back, go back and look at those vulnerabilities, inheritance, polymorphism, overloading, conversion, exceptions, dynamic, virtualization. Address those, build your standard, read DO332, or look at the AFuzion white paper. You can download that at the very end, we'll show you. And absolutely use modern tools like Solid Sands, experts such as AFuzion to help you out. Okay, so now I'd like to turn it over to Dr. Beamster, my colleague and friend, and he's going to give you the real secrets of how to utilize this in the real world. Got it? Marcel, it is all yours.
Thank you, Fons. Let's see if we can make this transition work. Can you see my screen?
Perfectly.
All right. So let me tell you a little bit more of where we come from. So Solid Sands started about 10 years ago, but we have a test suite that has a very long history. It even goes back to before C was first standardized in C89. And that is our bread and butter. That is where we started, really a product oriented toward verifying the quality of implementations. But over the coming years, and in the past 10 years, the industry was asking us, can you also help us with the safety of our implementations? And then we can look at compilers, we can look at libraries, and that's where questions came from as, okay, show the requirement traceability of your test. And though we had that at the course level, we didn't have that at a very fine-grained level. So we learned how to do that, and that led to the second product we have, SuperGuard. So these are the two products we have, and we are really a product company that helps our customers. And of course, we can show people the way of how to do safety in different processes and different projects. And that is, basically what we have learned on the job, this safety. So Fons is much more an expert in the standards of safety, functional safety. We come from the side of quality, and we've learned to apply our knowledge in quality and our expert knowledge of C and C++ in this safety area. Okay, I want first to tell a little bit about this requirements-based testing, because our background, our knowledge of safety is mainly applied in the automotive industry, also rail, robotics in general, but it's a bit different from aviation. However, both in aviation and in all these other areas and industries, we need requirements-based tests. And we have made those specifically for the C++ library, also the C library, but today we're talking about C++. So that level of requirement-based testing is here in the middle of the V model. Often the V model has more arrows, but I don't like those arrows. Of course, on the left side, we see how we have a very high-level definition of the software. We turn that into detailed requirements, and from that, you can build an implementation. So there's arrows there, but in general, in a product, you have to, in the process of a project development, you have to keep this whole V stable and consistent all the time. It's not like starting implementation and then much later starting with validating that implementation. You have to grow that together. That is easier to maintain and also much easier to manage. On the right side, we see the validation and the testing. So at the bottom level, we have static analysis. So there, Vance already mentioned, you need to have guidelines of working with C++. He mentioned the number of vulnerabilities. You have to address those, and some of them can be addressed by automated tools that verify your code to see that that code abides to the guidelines you want to follow, and you have to follow. The mid-level, and that is where we get to the C++ library. Of course, you can also apply that to the application, but this is where this is where our bread and butter is, requirement-based testing of the C++ library. And I want to go into a little bit more detail of what we mean with requirement-based testing. So what we, in the end, in this VML model try to do is that the right side here provides evidence that our left side has been properly handled and taken care of. Now, this is a very powerful mechanism. We do that at different levels. There can be more levels if you have a more complicated project, but basically on the right side, you try to collect evidence that all of your requirements and all of your code has the right shape and is verified and tested. And with that evidence, yeah, you can go through a certification procedure. However, there is a weakness in this model, because who says that our requirement-based testing, our tests on the right side, are complete enough. And for that, there's this crucial step of code coverage analysis. That's also automatable. You can, with code coverage analysis, you can run your test on your implementation, your, in this case, the C++ library implementation, and verify that you have tests for all of the code that is in there. And what it tells you is that if there's something missing, yeah, that might point to a missing test on the right side, but it may even point to missing requirements on the left side, because often when an implementation is happening, the implementer, the programmer, the developer, they make decisions about certain implementations, and they may introduce, maybe subconsciously introduce additional checks, maybe additional decisions, additional cases, which were not in the original requirements. And they may seem perfectly logical for the implementer, the developer, but if they're not described, then there's possibly no test for them. And if there's no test, you have no coverage. So with code coverage analysis, you can trace this back and puzzle, okay, what did I forget here? Did the implementation do something that was not in the requirements, or did I simply forget the test? Okay, next step, C++ is not C, and yeah, Vance already introduced quite a lot of that. I want to get a little bit and go back what yeah, Jonas Strausdrup said in an interview not so long ago, reflecting on C++. And he said, yeah, what C++ is really about is raising the abstraction level of C, because yeah, C is a very low level language. It's close to the hardware that has very many benefits, but sometimes you want to have more, yeah, more efficiency in programming. You want to reuse parts that already exist. You want to use higher level libraries. And that is what C++ promises, to be a more abstract C. You can still have the hardware access, but you can also have this abstraction. But the second call here, and that he made that very explicit, is to keep the efficiency of C. And that is the challenge that C++ addresses, and that shapes the way the language is formed, and it shapes also the way we have to deal with the language and with testing the language and with the libraries. So these two principles, they turn into this abstraction principle, the zero cost abstraction principle. We do want to have our abstractions, but we don't want to the efficiency of our applications to go down. So zero cost abstraction principle. And that means, well, there's a lot of things what that means, but these are the two sort of highlights there. And these are the things that we run into when we do the qualification work for the library, the C++ library. One is that C++ introduces templates, and templates are defined in the headers. And instead of introducing polymorphic objects, the templates make sure that every type instantiation of your polymorphic type, polymorphic class, is expanded. So there's an expansion of for every type and every explicit type that exists and is instantiated. Now that is going on behind the scenes, and sometimes that makes your compiler slower. You may have noticed that, especially if you have a complex project with many libraries. But that is happening behind the scene. The compiler takes care of this, and that means, okay, we have plain types again after the expansion, and the compiler makes sure that they are as efficient as any other type. The second helpful mechanism is the const expr use in function definitions. And they say, well, this function, you can execute it at compile time. If you know what the arguments are, then whatever the arguments are, that defines the result of the function. And so compile time evaluation can be introduced. And that means these const expr functions can also be used in template matching before any code is generated, before any runtime is happening. But that in turn also means that yeah, we see a little bit less of what's going on in the compiler. You have things going on in the compiler that you may not be aware of. And that means that, yeah, this abstraction is very high and good, but you may lose something as well. There is a cost to this abstraction, and you have to be a bit of, yeah, you have to be aware of this trade-off that you're making, because the traditional model of library code is lost in the C++ header and headers, the C++ standard library. And arguably that is a sort of a worst case example. So the examples that I will show you later are maybe a bit exaggerated, because in normal code you can tune down much of the abstraction that you're using, still to a usable level, but not as extremely as it is done in the library. But the library, traditional model of a library as a binary that you link to the program, that is lost. Much of the code is now in the headers, and the compiler sees that first and integrates that with the application code before any code is generated. That means that when you do your verification checking, like code coverage, which I showed that is needed to show that our test suite is complete enough and our specifications are complete, that also must consider the headers. It cannot just compile the binary library file independently from the application. These is all mixed together now in the name of keeping the efficiency. And then the final point that has quite some impact is that in aviation, other than the world of automotive, where most of my experience is, in aviation, you cannot so easily trust the compiler. If you go for a high safety level, then compiler is not something you can verify. In aviation, a compiler, trusting the compiler means that you really have to show that it's perfect for all possible inputs, but you cannot enumerate that. So instead of trusting the compiler, you have to look at the assembly code. You have to check that your source code is correctly translated into assembly code. And that is where abstraction is going to hurt you if you take it too far, because whatever is there in your source code is not a one-to-one match to your target assembly code. So what is generated for on the right side, if you take the array header implements, should not be a .h. Okay, mistake in the PowerPoint. That's the array header from C++. It gives you a nicer form of arrays. They are as efficient as the C arrays, but they give you additional mechanisms. But that means that when you write something like a subscript operation in an array, there's things going on behind the scenes that you may not be aware of. And I'll show you an example there. What is defined for accessing an element in an array here with a subscript operation, you have to understand what this subscript operation does. And if you then look into the C++ specification, you will not simply find a list of requirements for this index operation. The C++ standard is very precise and very accurate, but it is also not easy to read. And yeah, if you take this example, if you want to know what this index operation does, you look, okay, where is the operator, the index operator defined? Okay, that's in a table somewhere in the array template overview, but there's no explanation there of what it's supposed to do. So if you look for that, you get into a generic table. That's this table 88, and there it says, well, this a subscript operation is actually translated into this operation on the right side. So the dereference of the a.begin plus n, and then to understand this, you have to understand what means a.begin here, what is going on here. So you look further and then you see that a.begin returns an iterator, which refers to the first element in the container. And then this plus over here, it adds a value to an iterator. What does that mean? So you look further into the iterator and then you find out some abstract piece of code which says this is what it actually means. Basically make a copy of A, and then it's still an iterator and adding a value to the iterator. So then you have still to figure out what is this addition operation on the iterator. So there's a further interaction. What I want to get at is that yeah, if you're validating the C++ library and you want to extract the requirements for something as simple as an index operator, you have to look through a lot of abstractions and a lot of definitions that are all over the place. They're not in one place. So you have to learn to understand that when you want to do C++ library verification. Now, as I said, for more normal application code, it will not be as dramatic. Okay, I'm going to tell you a little bit more about some requirement-based testing things that we run into and how we develop tests. Show you a little bit more in depth about code coverage, MCDC coverage, and finally a remark about exception handling, going back to what Frans already said about exception handling. So the first one on this list, a specification of C++ is not the same as a list of requirements. Okay, past that, we've seen that already. Next, traceability, and here I show an example of the generated results, the generated report from the qualification, from the verification of this array header. So we have tests for the array header, and yeah, this is our report that shows the traceability of the results. And first of all, I want to point you out that for the array header, just that array header, we have a report of 295 pages. Now, part of this has to do with the fact that this is a container type, and container types are defined over many different types. And that means that in your testing, you cannot just test an array of integers. You also have to see, well, does it behave well with an array of doubles? Does it behave well with an array of objects? Does it behave well with an array of arrays? So these are all variants that you have to consider in your test suite, and you have to find representative examples of your test. And because you don't want to mix too many tests into one test example, because if one fails, you don't have proof for the others, you want to split them up. And that leads to this 295 pages here. Second, here we're looking here at the operator, the not equal operator for the array. There's the declaration for that operator, and on the left side here we see where that comes from. So there's a specific place in the C++ standard, of course, where this operator is defined, just like the index operator was defined at the place just before. And based on what is written there, we have derived the requirements for that operator. Now, there's not just one requirement. This is just one requirement, but for every function, there are usually a number of maybe 1 to 5 different requirements, or if this is a complicated subject, then there may be even more requirements here. But the requirement in this case, it mimics what is written in the standard, which means that the not equal operator is actually defined as an equivalence to another operator. And that is important because that means the not equal operator is really grounded in that other definition. If you would, that other definition would change, it changes the meaning of the not equal operator. And then finally, on the right side, well, for before last column, we see our test specifications, and they describe how are we actually going to verify this requirement. Final column is, of course, the result of the test. But in the fourth column, we have a couple of repetitions, but these are the variations that we see for different arrays. So we see an array of longs with a certain size, an array of ints with a certain size, an array of objects of type SOSA with a certain size, and all of these variations together give us the coverage that we need for the array object. Okay, then when you think about what do we need for developing tests, first of all, you look, of course, into the requirements. You have to find what is the definition of a function, what is it supposed to do. Then you have to find out what are the domains that this function operates on, and pick representative values on that domain. So if you have something like a value domain, that red arrow, red line over here, you have a minimum value, a maximum value. Those are boundary values, boundary cases. And then between boundary cases, yeah, you pick a number of representative values that you think, okay, they match well with the scope that I want to verify. Sometimes in the case of small domains, you really want to enumerate every single case, and that's then possible as well. So that may also be the right solution to go for. And finally, that also depends a little bit on experience of the test developer. For example, if you copy an array of 5 length into a specific space, the standard will not tell you that the 6th element in the target array is not changed, because the standard does not define things that should not happen. The standard only specifies things that shall happen, and everything that it doesn't say, that should implicitly not happen. But if you are a programmer of C and C++, you know that a one-off error is very easy. So you will also add a test that verifies that that 6th element is not changed. Okay, now a little bit more about code coverage. Why would you do code coverage? First of all, you could think, well, I want to assure that every bit of my code is executed by a test. So just to get the code coverage done, to get every piece of implementation covered by at runtime by a test. Now that's a very bad motivation. I alluded to that before already. If we have this code, for example, where we try to get the location based on 2 different kinds of accuracy, we can either use maybe a GPS or satellite location, which is maybe more expensive, takes more time, or we can use a low level precision for the location based on a cell tower location. And you can write the first test here, get the location under high precision, that's at the bottom of the line here, and then the green lines on the right side show, okay, this is all the code that is touched by that test that we have now at the bottom. Now that's not all the code, so we add another example, and that adds more coverage to our code. And then, well, this looks pretty okay, and we could be happy here. But if we go for the full report, adding everything together, we see that we have something missing, and that is the final else case, which returns in false. If the input is not high or low precision, maybe there is a 3rd value, maybe this is some undefined value. In C++, if you are careful, you can avoid that by using classes and inherited classes that only have the right number of cases. But in the case of more enum-like precisions, that can easily have a mismatch. And then you find out, okay, there's a mismatch. Now, that can easily be solved by adding that other location, but that is not the right way to do it. What you really want to make sure in your code coverage analysis is to ensure that for every test you have a requirement. And so if you have missing coverage, that means that you either have a test missing or even missing pieces of the specification, because it may well be that the specification does not mention this 3rd possibility at all. And the programmer here, the developer, was wise enough to include this fallback case, but there's no matching requirement there. And if you run into that, you have to go back in your V model and make sure that you have a proper requirement there too. So code coverage is helpful all over. Now, code coverage is not easy to implement in C++. This is an example where this is from the initializer list, and the initializer list has this end function over here, and it is from C++ 14. It is a const expr function, which means that it's compile time evaluable. And that poses a problem for code coverage analysis, because code coverage analysis want to insert instrumentation over here. But const expr doesn't allow any side effects for that instrumentation. So you cannot do that here. And that means you have to invent tricks and workaround and etc. it's not as simple as it was in C to get this code coverage analysis going. Another problem is, yeah, this is a quite extreme example from the tuple header. And this is just a simple, well, I should not say simple here, but let me see what this is. This is a constructor for a tuple. Yeah, over here is the name of the constructor, tuple. But all of this yellow stuff, that looks like code to me, and that is code, but this code is never going to be executed at compile time. At runtime. This code is going to be executed only at compile time inside the compiler, and that means that you cannot get any trace of the coverage from testing. You may or may not be executed in the compiler, but that's not traceable with code coverage analysis. And finally, exception handling. Yeah, exception handling is very tricky in C++, especially in combination with MCDC handling. That means code coverage analysis, statement coverage analysis, with the additional requirements. Yeah, you have to take care of all your conditionals and all your possible branches in your code. And if you have exception handling, then you create branches in your code. Now, two obvious branches in this code are here. There's a function call over here, and this create function, it may jump out of it with an exception, or we have this slink thing over here, another function call, and it also may jump out in with an exception. So that's a good start, and that would be fine if this was all. But in C++, we have operator overloading, and that means that every operator over here can be overloaded by a function which potentially returns with an exception. And I say potentially because in practice, this will not be the case. In practice, most of these operators will be just what they look like, will be defined probably by functions that are no experts or except, which means they cannot throw an exception. But the point is, you don't know that if you look at the code like this, and the analysis tools, code coverage analysis tools that have to help you with this analysis also do not show you this. So they cannot weed out this full, I would say, forest of branches that potentially exist in your code. So yeah, then to make sure with your testing that every one of these branches is covered is impossible, because most of them will never can never generate an exception. But that makes the analysis extremely complicated. If you thought this was a lot, this is not even everything, because in C++, even the comma operators can be overloaded. So we have even more arrows here. So my advice for writing C++ code in order to avoid this forest of branches, don't use exception handling unless you know very, very exactly what you do and what you intend with that exception handling. That's also the recommendation that Vance gave you. Don't use exception handling as a catch-all for everything. Make sure you precisely know what's going on when you use it. So this is almost the end. This is where I want to end with some take-home messages. C++ is not simply an extension of C. C++ is really a different beast. And that is why DO332 exists, to give you handles to work with that additional, well, let's call it abstraction. Requirement-based testing with traceability. We have that for parts of the C++ standards. So not everything we have covered already, but we have done quite our best to make sure that the most frequently parts of the C++ libraries have requirement-based tests. And if you need to use those libraries, yeah, give us a call and we can probably help you with that. Furthermore, yeah, those templates, they are very complicated, and they're especially complicated when you're trying to analyze the standard library, which is what we have done. But normal code is not so weird as this. So you can, with the guidelines that Vance gave you, you can make your code more manageable, more analyzable, and more understandable, both for you and for future developers, future maintainers, and for the tools that you use. And finally, yeah, talking about tools, you have to make sure that the tools that you use, work with the type of C++ that you write. So not all the tools are the same, and I'm talking about static analysis tools and code coverage tools, and they have to work for the kind of C++ that you write. They have to fit your workflow. They're there for you and not the other way around. And there we are then at the end of our webinar, and I want to hand it back to Vance. And
Fantastic.
the sun is shining at your place.
Yes, it is. The sun is finally up. I've had a few glasses of coffee. We've got a few nice questions, folks. We will have time probably for your questions. If you have more questions, we've got a number already. Please type them in to the question dialog box, not the chat box. Marcel and I use that, but the question box, okay? Let's begin with the first one. What code coverage tool would you recommend for C++? Marcel, why don't you take that one?
Yeah, I thought that would be a question for me. Yeah, we have looked at quite a number of code coverage tools, and that fits very well with what I just said. There is not one that fits every use case. The first kind of differentiator for code coverage tools is that the ones that instrument the source code, and they have this problem with the code, the const expr insertion. And then you have the type of code coverage that instruments the binary, and they don't have that problem. But the problem with the binary cases is, again, that you don't see much of the stuff that's going on in the compiler. So whether or not you need one or the other type of code coverage, that is already a choice to be made. And then there are a number of open source tools which are excellent when it comes to quality. But they may not be available for your platform because they have a limited application area. And then there are a number of commercial tools, and they all have their strengths and weaknesses. So it's not a one size fits all question and answer to that. So yeah, you have to really investigate that a bit, and it's worthwhile to do that because this is an important topic, I feel, for C++. Thanks.
It's a really good question. If I might add, in aviation, the latest version of 178, the version 4, it's called 178C, DO 178C. It's almost identical to the previous version, 178B. One key difference is paragraph 6.4.4.2, and yes, I have that memorized. You must do structural coverage on requirements, okay? So you cannot simply run a structural coverage tool and say, hey, look, I got it. Microsoft testing, sorry, Bill. Gates, yeah. We got 90% coverage. We have no idea what it does, but we covered all the bugs. No. You have to show you don't have bugs by tracing those, the actual coverage, decision conditions, statement, MCDC, for level A, to the actual requirement. Okay, so don't forget that. And Marcel brought that up, Dr. Beamster, in that requirements-based testing. Okay, so a really important key, especially with OO. We can't just be creative hackers and create these objects that don't have any relationship to the traced requirements. Okay. Next question. Oh, bookkeeping question from who we received the slides as PDF. Peter, everybody, sorry about that. American legal system. Yeah. Once we put them out as PDFs, there's some question as to public domain. However, on this last slide, coincidentally, you can see those two QR codes. You can download free white papers from Solid Sands and AFuzion. We've got a big library of 30 papers. Most of that information is in there. We've also seen some of our slides in the past on the internet, not by people taking screen grabs. So to be honest, you could simply go back and look at the recording, grab every screen and make your own PDF up. Well, you can do that. That's not a real ethical thing to do, but we're not going to come after you. Okay, so that'd be one way to do it. Next question. If I follow, if I adhere to all MISRA C++ constraints, rules, am I not compliant with DO332? Ooh, no, you're not. You have to do more, and without fully explaining DO332, we don't have time. There's a lot to OO and software that you have to do. It's in the 100 pages of DO332. You can read the OOT AFuzion white paper on the QR code for more information. It's a good start. You should definitely do it. You should definitely use the tools from Solid Sands here, no question. But you still need to do more. You have to show consistency among developers. You have to show traceability and that you followed the process. And remember, when you do a code review, and you always do these code reviews, there's 6 inputs to a code review. You got to use all 6, and that's pretty basic 178, but good start, but not completely. Oh, this one's for you, Marcelo. Compiler qualification for aviation is a difficult process. Do you think this can slow adoption of C++ in aviation software?
All right. That's a lot of packed into one question. Let's.
Happy Wednesday.
So yeah, my background is in automotive, and in automotive we see quite rapid adoption of C++ because there's all these sensors added to the car, and they all run libraries that are written in C++ a long time ago, and people want to use those libraries, and that brings in the need for C++. And in the automotive industry, we have the luxury, and that falls under the whole 61508 umbrella, that there is a special section about compiler qualification, which allows you to develop enough confidence in the compiler in order to be using that. And that helps because you don't have to take a look at the assembly code that comes out of the compiler. In aviation, there are much stricter rules for the compiler, and correct me if I'm wrong, Vance, but that is, as far as I know, DO 330, and it basically says, well, if you want to use a compiler, you better make sure that it is perfect. And that is a hard sell, and that is a very difficult case, and which means in effect that you still have to do this checking of the assembly code, but with the additional abstraction of C++, that is not so easy anymore. So it is really a new domain, as everything in object-oriented programming. If you want to apply that, don't underestimate it. It is doable still because yeah, many of even this array index operation, which has this very convoluted definition in the C++ standard, in the end it's just a dereference operator of an address. And if you know your source code, your C++, and you know your assembly, then you can match those and you can figure out that it's done in the right way. But yes, it may not be as easy as it is in the automotive industry. So but it's a challenge, and that makes us also, yeah, we want to make sure that these things are safe and to be able to use them in a safe way. Thanks.
Very good. Thanks, Marcel. Boy, we're getting a lot of good questions. Keep them up, folks. Is C++ commonly used in aviation? And if so, what type of applications? Is it used much in avionics? This is from Clinton. I'll take that one since AFuzion's focus is only aviation. You know, Clinton and everybody, 20 years ago, I predicted that by 2025, 90% of all avionics would be written in C++. Whoop, I missed that one extremely. Today it's about 30. And it's not because we shouldn't be using it or it's not better. It really is. The problem is legacy tools, legacy engineers, older people like me who are less comfortable with C++, and a lot of legacy applications. How many of you right now are working on an all new application? Not the majority. The majority of our work in engineering, they did not tell us at university, would be updating someone else's software, right? Well, that someone else's software was written in C. And by the way, you're behind schedule already and over budget. So easiest thing to do is just go back and reuse, and later in the future, you'll re-architect it to C++, right? Well, if you have a new project, use C++. If you have a complex project, use C++, bite the bullet. But the applications we're seeing it is on new aircraft. And we've got non-disclosure agreements, but I can talk about one that we're heavily involved with, AFuzion. It's FLRA, F-L-R-A, Future Long Range Attack Aircraft, the largest new project underway in the US right now. It's a rotorcraft helicopter attack, And about a fourth of the systems, the complex ones, some radar ones, missile one, is being used C++. We've also got a project we're doing in Japan, Israel, Turkey, New Zealand. They're all using C++. Southern Europe, we're doing more C. Northern Europe, more C++. Interesting kind of culture. So I'm going to predict, Clinton and everybody, in 5 years, everyone's going to be using C++. Okay. That's wrong. Next question.
Good luck with that.
Yeah, seriously. Thomas asks, as an ISO 26262, that's the standard for automotive, came from 61508, which came from 178, qualified compiler ever been used successfully without source object traceability or object level coverage that 178C calls for? Marcel, do you want to take that one?
Yes. The answer is yes. Compilers are can be qualified and can be certified under ISO 26262, and they don't require you to open up the compiler and look inside. So these standards, they do allow you to treat the compiler as a black box and check the input versus the output. One of the reasons why that is doable is also that compilers, in the end, they are not non-deterministic machines. They are very complex inside, but they are also, for a given input, you get a certain output, and that is a one-to-one translation. So they're very repeatable, and they're very, in that sense, approachable and well testable. That they behave well in a testing framework. And so if you have a test suite like ours, Supertest, then you can get a long way there. Of course, you still have to show that your test traces back to the definition, the standard, and you have to do your work on the process. I mean, the process is not just running a test suite. You have to do your documents. You have to follow the process. But in the end, you can get compilers qualified for the highest safety level in aviation, not in aviation, in automotive, which is ASIL D.
Very good. Thank you, Marcel. Umut asks, are there any C++ constructs that you recommend not using to avoid problems when meeting Objective 9, verification of additional code, the dead code, deactivated code paradigm in 178, in table A7 of 178C DALE? That's everybody. That's simply a 178 construct to ensure that you don't have unwarranted code, that you don't have any untraced code. All code for level A, B, C has to have a reason to be there. And again, that reason is 6.4.4.2 of 178, have requirements-based testing. So Marcel, what constructs would you recommend people try to avoid, especially to avoid deactivated or dead code?
I don't think I'm using my experience here as a compiler developer. I have not looked into this specific topic before, but as a compiler developer, I would say that C++ compilers are probably a bit more careful about generating that code than C compilers, because there's so much going on in the header files and there's so much pre-compilation there done. So if you have an object defined in a header, you use only one or two of the functions there, the others are not going to appear in your code. So there's a more weeding out of code already early in the process of compilation. And yeah, the idea of C++ is still not being wasteful and not being inefficient. So the C++ compiler, although there is stuff going on under the hood, maybe more so than in C, it's not like it's generating code that should not be there. It's really is there for a reason. So I don't have something there that comes up exactly now where I would say don't use that or don't use that. So that's my best guess here.
That's a good answer. I would add also, from what I've seen when we do a lot of audits or reviews or we mentor clients, two aspects of C++ that are dangerous and overused. Number one, polymorphism. It's cool, right? Multiple inheritance, that's really cool. Yeah, try doing traceability and verification of someone else's very obtuse code. Another one is simple inheritance. You know, we've seen projects with 10, 12 levels of inheritance, right? My goodness, folks, it's almost impossible to trace and keep in mind. And you finally built up a mental image as you're modifying this code. And someone comes into your office and says, "Did you see that football game yesterday?" You've lost it all, right? So I would be very careful on that. Don't get too fancy. Remember that we've all had situations, if you have gray hair, where you looked at code and said, "My goodness, who wrote this crap," right? And then you realize it was you, me, 4 years prior, and you don't have any recollection, okay? So that's what good architect commenting and coding standards following DO 332 will hopefully give us. We got another question. Oh, here's a fun one. How to convert source code that was not developed to 178, but you have to make it 178C compliant, and the source code is C++ Java. I'm going to take that one up, or so you can embellish the answer if you'd like. And we've got time for just one more question after this. Okay, so I would start with Java. I love Java. The challenge with Java for level ABC is a coding standard, a recognized FAA EASA acceptable coding standard for Java. They're very much hard to convince, FAA EASA, and we teach both FAA and EASA a couple times a year. They're conservative. If there's a plane crash, you know who's going to be knocking, right? So they're ultra conservative, too much so, but that's their job. So Java I try to avoid. I would port to C++. Now C++, I would use tools like, Solid Sands, do the static analysis. First, make the C++ code compliant to MISRA, pass the tool checks, Solid Sands, etc. And then I would document the heck out of that code with consistent function headers, consistent comments, and I would then reverse engineer the code to meet the coding standard, okay, which is automatic ready MISRA compliant. And then I would reverse engineer the requirements, and I do traceability at that stage from low-level requirements to the code, and then I'd fill in the design documentation and high-level requirements. Marcel, anything you want to add to that?
Yes, what comes into mind is experience that we had with the C library verification. So that's the implementation of the C standard library, where, well, the C standard library, there are a number around, also in the open source, and they are not written with functional safety in mind. So they did not adhere to MISRA standards or any other well-defined standards, although these open source projects, they do have their own guidelines and they do have very high quality levels that they have to adhere to. So what we find sometimes is that, okay, that code is actually very well engineered and battle tested out in the open. And if you would re-engineer that and try to make that conformant to MISRA standards, there is quite a likelihood that you introduce bugs in there. So the solution there is not to completely forget about MISRA checking and not doing the standards, but to make sure that you tune the guidelines to the code that you're using. And MISRA has a number of required rules and a number of optional rules. So you try to stick to the requirement rules, but for the optional rules, you want to make sure, okay, if I leave that out, is that a security hazard or a safety hazard in my code? And if that's not the case, you can look at, okay, where does this code violate these rules, and can I have justifications for that? So that's a little bit the opposite around, that you're sort of adapting the guideline to the code. But in some cases, code can be very complicated, and you may say, I don't understand it, but it may still be very well engineered and very hardened code that just works and has a long history of serving in many different application areas. So there
Good point.
both ways. There are two sides to this coin.
Very good point. Folks, we are at the top of the hour. Sorry we didn't get to all your questions. There's an infinite number of questions. There's an infinite number of possible C++ source code constructs. What you learned today is hopefully apply the standard, use great tools like those from you got at Solid Sands, get good advice, and be safe out there. Thanks, Marcel. Thanks, everyone. See you next.
Thanks, everyone.
Thanks, everybody.
Bye-bye.
Bye-bye.